Let's dive right into this explainer. Today we're looking at Aurora ZK governance, and specifically how we transition from a basic MVP to an absolute cryptographic fortress. If you spend any time at all building in the Web3 space, you already know that wiring up a zero-knowledge governance system is just a completely different beast compared to your standard smart contracts, right? It demands this delicate, almost paradoxical balance. You need complete on-chain transparency, but at the exact same time, absolute voter anonymity. It's tricky. So how exactly do we pull this off? How do you upgrade a DAO from a super fragile prototype to a legit cryptographic fortress? That is the fundamental challenge for us as developers. How do you take off the developmental training wheels without the whole bike just falling apart? Look, when we first stand up a DAO, sure, we use mock components to get the skeleton working. Makes sense. But if you take that MVP simulation into a live, hostile environment, come on, you're going to get exploited in minutes. We absolutely have to rip out those placeholders and swap them out for battle-tested, verified zero-knowledge proofs.
We can actually map this transformation out as a chronological, evolutionary blueprint across 3 distinct sprints. It's really cool to watch this system mature step by step. So, Sprint 1, that's our skeleton phase. That's where we're just establishing the basic flow, using those fragile placeholders I mentioned. Then we hit Sprint 2, and this is where the real magic happens. We build out the cryptographic backbone using actual circumcircuits. And finally, Sprint 3. That's where we implement the full governance runtime, locking down that execution layer so we are completely ready for a public testnet deployment. Let's break this down, starting right at the foundation, the core cryptography.
Okay, so back in Sprint 1, we leaned heavily on Ketchok 256 for rapid prototyping. And hey, Ketchok is the absolute workhorse of standard solidity, right? We all use it. But drop it inside a ZK circuit, it's an absolute nightmare of mathematical constraints. It's just too heavy. So moving into Sprint 2, we have to pivot to Poseidon. Poseidon is highly optimized specifically for zero-knowledge math. It requires way fewer constraints to prove, making it our secure, ZK-friendly production standard. And here's the exact recipe to lock down those early privacy gaps. We take a Poseidon hash, and we mix in the specific proposal ID, the current governance epoch, and the user's private voter secrets. This specific cryptographic cocktail is brilliant because it guarantees a user can only vote once. But since their secret is never actually revealed on-chain, there is zero chance for some blockchain sleuth to link their votes together across different proposals. What we're generating here is a deterministic nullifier, and this is your ultimate shield. Think of the smart contracts like a blindfolded bouncer at a club. When it processes this unique hash, it simply checks it off a list. If that same person tries to vote again on the identical proposal, the bouncer feels that exact same hash and immediately turns them away. It flawlessly enforces the one vote per proposal rule without ever knowing who is actually standing at the door. It's kind of amazing. Now, to actually make all of this work, Sprint 2 relies on a specialized roster of 3 core circuits. You really can't just have one massive, clunky circuit trying to do everything at once. Instead, we break it down. First, you have an eligibility circuit acting as your binary gatekeeper, just proving a user is an authorized member. Then you've got the vote circuit to generate those nullifiers we literally just talked about. And finally, you need a trust circuit to handle the complexities of reputation. Let's talk about that trust circuit for a second, because it patches a massive vulnerability: trust score leakage. This circuit proves a user belongs to a specific tier, rather than leaking their raw exact reputation score on-chain. Think about it. If your raw trust score is exactly 87, and you happen to be the only member in the entire DAO with an 87, well, anyone watching the chain can instantly de-anonymize your vote, right? So by abstracting that exact score into a broader bucket, like say tier 3, the trust circuit completely eliminates that leakage. Problem solved. But to actually get this into production, we've got to rip out the hacks. During the prototype phase, it's super common for devs to use fragile placeholder methods, like literally slicing up call data manually just to decode the user's tier. It works for a quick test, but it is highly insecure. For real production, we modify the circumcircuit to explicitly output that trust tier into an array called public inputs. This lets our smart contract read it safely, natively, and with full cryptographic verification. And once we have that tier safely extracted, we can finally fix a critical logic bug from the MVP. Our final arbiter, the ZK governance contract, can take that mathematically verified tier and use it to properly scale the user's voting power. So, Tier 3 members get the heaviest weight, while Tier 1 gets the lowest. It's simple, it's secure, and most importantly, it's cryptographically proven. All right, so moving into Sprint 3, the governance runtime. Here, the policy registry steps up to manage the lifecycle of these verified rules through a really strict three-step process. We are completely moving away from hard-coding rules directly into the voting contract itself. Instead, the policy registry becomes the ultimate on-chain source of truth. First, we deploy our real Solidity verifiers and register them with a version string. Next, we explicitly activate that bundle so the DAO actually starts using it. And step 3, we freeze it. That locks the policy in place and totally prevents any tampering down the line. The absolute game changer here is that this decoupled architecture means you can safely swap out a mock verifier for a production-ready one, and you don't even have to rewrite your core governance engine. Whenever someone submits a vote, the main ZK governance contract just queries the policy registry. It asks, hey, which verifier should I be using right now? And then simply forwards the zero-knowledge proof to that specific address. It makes the whole DAO incredibly modular, infinitely upgradable, and highly resilient. Now, once everything is active, the execution shifts to a two-stage flow. Approved proposals must be queued before they can actually impact the protocol. Listen, in a mature DAO, you can never, ever have immediate execution. The exact moment a vote successfully passes, the execution function stays completely locked down. The system grabs the targets, the values, the exact call datas, and throws them into a queue. This transitions the proposal into a very strict waiting period. And what that queue does is trigger a mandatory 2-day time lock. Guys, this is your ultimate failsafe. Let's say a cleverly disguised, malicious transaction somehow sneaks its way past the ZK voting phase. This delay ensures the community isn't just ambushed in the middle of the night. It gives everyone a full 48 hours to sound the alarm, deploy countermeasures, or, just properly prepare for a legitimate upgrade. But hold on, before you push a single button on a public testnet, you absolutely have to deal with the toxic waste. To secure those Groth 16 circuits we built, you have to run a Powers of Tau multi-party ceremony. This is what generates the underlying mathematical randomness for your proofs. Deliberately destroying that initial setup data, that toxic waste, is literally the only way to mathematically guarantee that absolutely no one has a backdoor to forge fake votes. You can't skip this. So, taking all of this in, I want you to take a really hard look at your own DAO architecture. Have you truly removed the training wheels? Or are you just hiding a super fragile proof of concept behind a shiny ZK buzzword? Transitioning to true zero-knowledge governance isn't just about the math. It's about systematic, rigorous cryptography at every single layer of your stack. The blueprint is right here. So what step are you going to take today to upgrade your system into a true cryptographic fortress?